Thank you, Marky, and thank you, Pedro, for giving me the opportunity to be here today. This is something.
No. Okay.
We are here because the South American region is located just under the so-called South Atlantic Anomaly region, which arises from the fact that the dipole magnetic field is tilted with the respect of the rotation axis. So, please next. When you are in Italy, you have a rigidity cutoff, which is of the order of 4 gigawatt, which means that the particles that are primary cosmic ray with an energy lower than 4 GeV cannot reach the top of the atmosphere, and so to produce cosmic ray secondary flux at the surface. Well, when you move to the equator and even below, as for example here in Bolivia, you have a rigidity cutoff which is higher. So in general, the local component to the dose which come from cosmic ray secondaries increase with the altitude, decrease with the rigidity, and can be modulated with the solar activity, especially when you are at the peak of the solar activity cycle. Next, please. But there is one more thing that we can take into account. Okay, due to the asymmetry of the geomagnetic fields, the two Van Allen radiation belts, which are two regions, toroidal regions, where the energetic electrons in the external one and the energetic protons in the internal one are trapped by consequence of this misalignment. So this means that in the inner belt we have the most energetic particles, which are proton at a few GeV level, that above the South Atlantic anomaly are not more than 200 kilometers far away. So that means that in this region you will have a significant increase of flux of energy particle, and so possibly also cosmic ray secondaries that can be dangerous for sorry. Can you go? Okay. Go back. They can be dangerous for spacecraft, satellite instrument, and astronaut as well. So, these belts are not a stable structure. Please go on. And you can measure the flux of primary protons trapped in the inner belt using a satellite detector. Pamela is one of that has been measured many times at different locations in the belt. The proton flux that can reach up to 2 GeV. Okay, next. So always looking at the data coming from the satellite detector, you can see here that most energetic protons are trapped in the interior Van Allen belt, just above the Bolivia and the Argentina surface. So the maximum energy that you can reach is just above our head now. Next, please. The problem is that the Van Allen belts are not a stable structure. They can be modulated by the solar activity. They can change over the time continuously, depending on the solar activity. And eventually, if you have, as you expect, a solar activity peak, magnetic storm that can release particles in the inner belt that can consequently can precipitate in the atmosphere, producing an extra cosmic ray secondary flux that can reach the surface. And this is one of the main goals that SAMADHA project can do. The eventual observation of this proton precipitation that can will affect the cosmic ray secondary at high altitude in the South Atlantic Anomaly region, and so contributing to an extra environmental dose that can affect the population that live at a high altitude in this region. I mean, you can imagine the people living, the million of people living in El Alto, or also in other cities, as in the minor city in La Rinconada in Peru. Next, please. Okay. So the second question: why doing this measurement on the neutron component secondary fluxes here and now? Because we are approaching the end of the 25th solar cycle, which is expected to have its maximum at the end of 2024 or beginning 2025. So, go back. Looking to the induced dose from cosmic ray secondary at Earth, we must account for a weight factor which is different from different radiation component, which is bigger for the neutron component because the interaction of neutrons with our body, our cell, can cause extra damage. But if you take a look to the equivalent ambient dose used to the cosmic ray to the different components, which are not only the electromagnetic components, but the hadronic component and in principle the neutrons, you see that you can see that moving from 0 to 5,000 meters, the neutron flux can increase more than a factor of 10. And at high altitude is the main component of the ambient equivalent dose. Which means that if you want to do this kind of measurement in the South Atlantic anomaly, you have to go up and you have to use detectors that are sensible to the neutron components, which is the main component of the equivalent dose when you are above 4,000 and 5,000 meters above sea level. Next, please. So we did it, and in a joint collaboration with the local support of people here at UMSA. So we have one project, two different laboratories to make an online comparison of the data that we can collect in both inside and outside the South Atlantic anomaly using a common set of instruments. Next, please. So first, the first laboratory, we made the test of our detectors is located in Italy. This is the Testa Grigia Laboratory, which is nearby the Swiss border, here, in the Plateau Rosa, which is a very big skiing area for people during winter time. It's located at 3,500 meters above sea level at an equivalent rigidity of about 4 gigavolts. It's not so far from the Torino, the city where I live and where I make my research. It's just a 3-hour trips from Torino, which include 45 minutes by cableway to reach the top of the Plateau Rosa region. Here in the back you see Monte Cervino, and here is the Mont Blanc, the highest peak in Europe. This is our laboratory that is in operation since the end of 40s, and is dedicated mainly to cosmic ray physics during 60s, 70s, 80s, and nowadays also for monitoring the contamination of the atmosphere. It's here that since October 2021 we test all our detectors, okay, also the ones that we have moved here in the Jakarta laboratory. Next, please. So here you can see a collection of the detector, explicitly dedicated to the neutron monitor. Some of them are commercial one, as these two red counters here, which are sensitive to the high energy neutrons, the one that you can search in the cascade process induced by cosmic ray. We have also those commercial gamma dosimeter, which is sensitive to the X-ray and gamma rays in the range between 15 keV up to 3 keV. We can profit of a modular neutron monitor, which is this one, smaller than the one that you have in Jakarta now. And also we profit of some in-house developed linear energy transfer device, which is a silicon-based, by which you can make the spectrum of cosmic ray, and so to calculate the equivalent dose. Next, please. Of course, if you want to have a proper understanding of the cosmic ray secondaries, you need also to measure atmospheric data. In principle, you must have the pressure, because changing the pressure changes the probability of cosmic ray secondaries can be produced in the atmosphere. So you have to disentangle the pressure effect from the cosmic ray effect. So a full equipped meteo station has been installed in October 22. We also put an electric field monitor in order to get information about lightning and storming in a wide area around the laboratory. And also, since the main goal of the project is to have online in real-time measurement of the neutron flux at the Earth, we also install a link with two antennas that you can see here that provide the connection, the full connection to the 5G network used by people studying. Next, please. The second laboratory that can be used for this kind of measurement, thanks to the collaboration with the local group here at Instituto de Investigaciones Físicas de La Paz, is the one that you know very well. This is located not so far from here, 1.5 hour trip by car from La Paz, at the equivalent rigidity of about 12 gigavolts, at very high altitude, which is almost 2,000 more than the one that we have in Italy. Next, please. And that's a collection of the instruments that we have there, which have a big overlap with the one which are running now in the Italian laboratory. So we have a RAM counter up to which is the equivalent of the one that we have in Italy. We have a LED spectrometer, the ones that have been developed in collaboration with the Praga Institute of Physics. And we have also, which is the golden nugget of the SAMADHA project, a bonosphere system, you can see here, okay, which provides not only the measurement of the neutron flux at our laboratory, but also the possibility to make the spectrum, which can be different during space weather effect from the local one, which can, which is mainly induced by the local radioactivity. So with this kind of instrument, we can make a monitor online. We can profit also the information that comes from the neutron monitor, which is working at the Testa Grigia Laboratory since 1964. And we can make a comparison of the neutron flux time by time online measured at Chacaltaya in southern Atlantic Anomaly, and comparing that with the ones that we can measure in other laboratory sites, so the one that we have in Italy, and at the moment also with some instrumentation that we have in the Antarctica running at the same time. Next, please. So we did it, and we started since last month on November. So we have an automatic, fully automatic system which provides data flux from the detector to our machine that provides the analysis of the data. Till the website that you can reach, which is open to the public, at which we can every hour make the analysis, the online automatic analysis of our data. I will show you some examples that you can check by yourself accessing to the website. Business. Okay, these are the data that's coming from Chacaltaya, from the instrument that we have there. So the run counter, which well, here you can see the modulation of the dose rate with the time. We have the LED spectrometer, which provides, in some sense, the cosmic spectrum. The low energy part is one correlated to the electromagnetic component of the cosmic ray, while the high energy part is directly connected to the nuclear recoil in the silicon detector, which is located here. When you have the spectrum, in some sense, you can convert the spectrum, weighting the different cosmic ray flux components, the electromagnetic one and the neutron one, in order to get the dosimeter, the dose rate equivalent versus the time. But the most interesting thing is the bonosphere system. That Luigi will show you in a moment. We have an online cross-check of the response of all these spheres in order to get if they run properly. Once you get the counting rate of the sphere like this, you can compare with some reference that we got at the end of the data taking in a moment where the solar activity was low. And so in this way, you coming from the counting rate of each sphere, you can unfold this counting rate in order to get the local Newton spectrum. About this detector, in a few moments, Luigi will give you some more detail in order to understand how this works and how it is performing in order to get the Newton spectrum. Last slide. Okay, so in conclusion, in this introduction, as you can see, with our joint collaboration with the Bolivian people, which are working hard and collaborating with us in a joint full collaboration, we try to make the environmental dosimetry and space weather study, which is two different goals of the project. We have an online and real-time monitoring of the data, which is expected to be interesting when we will reach the peak of the 25th solar cycle. That will be monitored at both sites and laboratory, both in Italian and in Bolivia. SAMADHA activity started late into 21, where we completed the test in 2022 of all our detectors, both the ones that we are running there in Italy and the ones that are at the present here in Bolivia. The active phase is already started in November 2022, where we in the first 3 years in Bolivia, we bring and we install part of the detector. And we come back later in March 2023 to install the Born sphere system to monitor the neutron spectrum. Okay. Of course, both side instruments need so sometimes it happens that we have to make maintenance of the detectors, as we did during this trip in Bolivia just now. And let me thank all of you, Martin and Pedro, for the great and fruitful collaboration up to now. So I leave the speech now to Luigi, that will give you some insights about the Bonafide system, which is the best instrument that we have right now running at the Testa Grigia Laboratory.
Thank you very much.
Thank you very much.
So maybe we can make questions at the final stage of the presentation. So I have the presentation of Luigi. Or?
You should have. Yes, I sent it by WhatsApp.
Okay, thank you very much. So just wait a little bit, please.
Can I start?
Please. I can see you. Let me take your presentation. Okay. Now.
So good morning, everybody. I am Luigi Russo. I come from another laboratory in Italy, always from INFN, National Institute for Nuclear Physics, but I am part of the Roma group. Today I will talk about extended range Bonner sphere spectrometer for neutron measurement. This is a particular detector that we installed in Chacartaya, and I will give you some details about this detector. So the SAMADHA Bonner sphere system is made up of 8 spheres. Each one contains an helium-free detectors with a sensitive area of 3 centimeters, 3 cubic centimeters, and a internal pressure of 10 bars. Each one of these detectors is triaxially cabled in order to avoid discharges or electromagnetic noise, and the sphere dimensions are kind of building, an innovative way of building, because we substituted the block of lead and the block of iron with some ballast in order to improve the transportation and availability of the material when we build the spheres. So why we installed Bonner sphere spectrometer with helium-free detectors? The detective principle of the helium-free is described here, because the helium-free, which is contained in the active area of the detector, reacts with the neutrons, the cosmic neutrons, not only the cosmic neutrons, but with all the neutrons, producing tritium and a proton. The Q value of this reaction is here, it's 764 kiloelectron volt. This energy is divided between the two products of the reaction. We have 0.573 megaelectron volt for the proton and 0.191 megaelectron volt for the tritium. why we chose to insert the Bonner spheres? Because alien detectors are sensitive only to thermal neutrons, but we are interested in measuring all the neutrons. That's why we call it extended range spectrometer, because we want to detect neutrons starting from thermal neutrons, so millielectrovolt, up to GeV neutrons, so fast neutrons, which is a working principle. The working principle of the detector is shown here. The neutron is initially moderated by the polyethylene, and then it reaches the active area where a pulse is recorded by the detector. If we increase the volume of the spheres, we have the possibility of moderating high energy neutrons, but we can have another problem, because some processes like this may happen. The neutron can be partially moderated and then stopped inside the polyethylene without giving rise to a pulse inside the detector, or it can be back scattered, and also in this case we do not have any kind of signal. The way in which we can extract the spectrum, a neutron spectrum from a Bonner sphere detector, is using response function. So each particular sphere is sensitive to a certain range of neutrons, because of the diameter of the polyethylene and of the lead and iron for high energy neutrons. So here is shown, I will explain you briefly how is made up the acquisition chain of the SAMADHA project for the Bonner spheres. We have our helium-free detector inside our spheres. We have our electronics, which has been recently substituted in order to become more stable for long-term data acquisition. We have our digitizer, which is connected, which collects the output of the boards, electron ports, and it gives us, using a LabVIEW-based software, the spectra of each one of the spheres. Everyone needs clearly power supply, because we need low voltage supply for the electronics, both low voltage supply for the electronics and high voltage supply for polarizing the helium-free detectors. And the innovative thing is that we don't have a continuous connection with the high voltage generator, because we want to limit the electronic noise coming from the electrical line. So we use a high voltage capacitor-based generator, which is charged every 6 hours by the high voltage generator, and for the other period, when there is the acquisition, there is no contact with the electrical line, so it may help in decreasing the noise from the line. Here I show the SAMADHA capture screen, the first capture screen where all the pulses are shown. So we have for each one of our sphere a display, the possibility to see the pulses. The pulses are, of course, Gaussian pulses, because there is a part of the electronics equipped with the shaping amplifier. So this gives rise to this particular shape of the pulse. And we have a second capture screen, which is the pulse rate distribution or the spectrum, of course, for each one of the channels. So there is an energy cleaning. Each one of these pulses is recorded in this spectrum, and it gives rise to a spectrum for each channel. But it's needed also a post-processing and a data cleaning process in order to improve to act as a filter for the signal that we have, because we may have good signal, which are Gaussian shape signal in the voltage that we consider good for our pulses. Then we have spurious signal, which may be not good and has to be excluded by the spectrum. And of course, we can have discharges due to electrical noise or internal process in the detector. So that's why we need also a post-processing for the data collected. So here I show a first kind of total spectrum that we obtained from Chakantaya measurement. Here is compared the reference week in April with the last week rates, the one weekly rate going from 15 to 21 November. And as you can see, there is a trend with a certain number of counts per second for each sphere. And starting from this, we want to start our spectrum. But this is not so simple. We need Monte Carlo simulations to obtain our response function, because as I said before, each sphere is sensitive in a certain way to a determined energy range. So we made some Monte Carlo simulation with the Monte Carlo and particles code. This is the geometry of the simulation. Here there is a neutron disk source. Here there is our detector. This is the detector only with polyethylene. This is the sphere only with the polyethylene. This is the sphere with also the iron or lead. And we obtain these, using the Monte Carlo, we obtain these response functions. But this response function needs, of course, a calibration process to translate this simulation into reality. So we did a calibration in the aberration variable source in Polytechnico di Milano with the shadow cone technique, which allows us to avoid to subtract the scattered part of the spectrum, and we obtain this energy distribution for each one of our detectors, including a comparison between the lead sphere with the solid unit block and the one with the balance. These results are very similar, and so we confirm the choice of the balance that are much more easy to transport and to obtain. So there is also a statistical part which allows us, starting from the spectrum of each one of the channel of our bonus sphere system, to obtain a unique spectrum as the one that is shown here. I will show in the next slide other spectra. This is based on the solution of this set of equation, which is an equation in which here we have the counting rate of each one of the spheres, and these are given by the total fluence multiplied by the sum of the n intervals in which the spectrum is discretized, and then you have the response function, which are the ones that we obtain using the Monte Carlo simulations, the fluence energy distribution discretized and normalized to 1, that is the one that we want to obtain, and of course the intervals, the energy intervals of energy. So the first experimental campaign with our bonus spheres has been made in Cervinia, Testa Grigia, the laboratory that we were talking about with Carlo presentation. We have here our system of spheres with our electronics. This is a first spectrum obtained after 2 days of continuous measurements. We did, of course, an unfolding process in order to obtain the neutron spectrum in this condition. Starting, you have to start from a gas spectrum, which is the one from which the software starts to work using some parameters, and then you obtain this kind of spectrum. And of course, we compare the two using two kinds of gas spectra. One in which the snow water equivalent is 20 centimeters, and one in which the snow water equivalent is only 1 centimeter. But the result in the spectra are seems not to be very influenced by this kind of gas spectra that we use to start our statistical process. Then we installed our system last March in Jakarta. Here we have our bonus sphere system, and here we have the dosimetric system. Also in this case, we start to analyze the data. Here we can find the counts per second for data taken from 1 week of low solar activity, which was this one, because we have a maximum neutron flux in this condition, and it was the week between 10 and 16 April 2023. So we started to analyze, as I was saying before, we started to analyze this data, and we find that maybe it's not very clear from the slide, because there was here a light blue evidence of the week from 10 to 16 April. and the yellow block for the week from 9 to 15 May. We see that since 8th May there was a sudden drop in the counts of all the spheres compared to the previous and to the subsequent periods. We investigated this decrease and we find some possible explanations. One is of course the snow in that period, because we had snowing phenomena, and another maybe the solar storm, so the Forbush decrease. But they act in a different way, because we know that snow is a good moderator for neutrons, so it may affect mainly the thermal and the epithermal part, reducing the flux of this particle. The solar storm Forbush decrease affects more the high energy part of the spectrum. Because if we compare, here we have the two neutron spectra, we compare 1 week of low solar activity with the 1 week in May of the sudden drop in the count per rate of each sphere. And we see that if we consider the cascade peak, which is the high energy neutron peak, we have a decrease of 5.5% in the cascade peak, which is consistent with those recorded for cascade neutron flux by other neutron monitor in other parts of the form. So, what we can say, we can start to reach some conclusion, but we have to investigate in a better way this part. We can say that the reduction in the thermal and epithermal continuums is mostly given by the snow phenomena. Instead, the cascade peak, the reduction in the cascade peak is very probably due to the Forbush decrease event. Another comparison that we did is, of course, the comparison between the Chakaltaya spectrum and the one obtained in Cervinia. We had some differences because, for example, the week from 10 to 16th April, there was no snow in Chakaltaya. In Cervinia, there is always snow. So, as you can see, there is a reduction in this part, in the low energy part of the spectrum. Of course, many other factors impacts on the difference between the two spectra. The two spectra are taken at different altitudes and with the different, but of course with the different, this effect of the altitude is partially compensated by the fact that we have a different cutoff rigidity in the two parts of the world. Because we are, as Carlo showed before, the magnetic rigidity is higher in the Chakaltaya station than in the Cervinia one. So, in conclusion, what we can say? We have this system of 8 spheres for extended range spectrometry. We have a custom electronics optimized to reduce spurious signal, usually arising from high voltage, alternating current power supply. We have high energy response using these lead or iron bullets that are a low-cost alternative to solid parts. We have a response matrix obtained with Monte Carlo simulations and verified in a calibration field, the one quoted in Milano. We have high elevation measurements in Cervinia. They show good results, and we needed only 2 days to obtain a good spectrum. We estimated both ambient dose equivalent and cascade fluids. We installed then the system in March 2023 in Chakaltaya, and we start with the unfolding of the first spectra, obtaining the first results. Here I added the first articles published by our group. We have many others. I hope we will have many other articles in the future to be published. And with this, I close my presentation. Thank you all for
Okay, thank you very much, Luigi, Carlo. And now we can maybe make some questions. Please.
Thank you for the presentation, it was really nice. I'm not sure when is this reduction of the neutron flux. Is during the snow precipitation or once the snow is on the surface? You will answer.
What's important is that the amount of humidity that you have, so the amount of the water. So when it starts snowing and it's try to accumulate, okay? So this will be act as a moderator effect of the particle, okay? In principle, in particular on the neutrons. So if you have stable quantity of snow, the reduction is a constant level. The change from the one that you have when there is no snow, okay? When snow tries to evaporate and so changing, decreasing over the time, the counting rate will be recovered up to the original level, okay? So in this particular case, we have two rare phenomena that happens together, and what we are doing, trying to disentangle the two components that we have at that moment. So the best that you can do is to have a stable condition without snow, okay? And so you can look directly to the space weather effect, as in the case of the purple decrease, or to other solar phenomena, solar activity. Simulation, you need to know how much is the time that you need to recover the original condition once the snow is completely disappeared.
Okay. Thank you very much. Someone else? Yes.
This kind of instrument. The first one is that when you are lighting the atmosphere, okay, the extensive shower producing cosmic rays secondary is affected, okay? So you have to distinguish the two components, the standard one, which is the process of extensive shower in a standard atmosphere, and the one that you have, we have at lighting, okay? You can improve it. So as well as you have to disentangle pressure effect on the atmosphere from the data that you have collected. So when you have lighting in an area which is around your detector, you have to account it. This is why we put also an electric field monitor in the Chakrataya laboratory, as well as we have in the Testa Grigia station. The second problem, the second possibility is directly correlated to the emission of radioactive nuclei. I'm thinking about radon that can increase when you have earthquake phenomena. Okay, this is some possibility that you have to can study with this kind of detector in correlation with earthquake. So what you can do is you have your reference neutron spectrum, okay, outside the earthquake times, and then you can make a comparison. If you do only by flux, it's very difficult, but if you, since the main component affected the neutron spectrum is only the low energy part, so the thermic and epithermal part of the neutron component.
Okay, thank you very much. Yes, Isabel.
One question. If the humidity is a modulator,
yeah,
would being into the cloud would be a problem?
No.
Or not a problem, I mean, something that affects the measurements, because we are often into the cloud, not necessarily with precipitation.
Yeah, but what is important is the local amount. So usually when you have precipitation, the quantity of humidity is higher than the one that you have just in the clouds. Of course, it's important to know it, but to disentangle this kind of effect, you need a very precise Monte Carlo simulation to do it. So we are, at the moment, we are far from there. So what we must know exactly, the first is the pressure, because the cosmic ray extensive shower production can change with the pressure. And the second one is to know which is the amount of water equivalent that you have in an area that could be big, so few hundreds of meters. It is the one that matters this kind of measurement, because neutron can scatter, so you can collect a neutron that can even far from the detector. Okay,
Thank you very much.
And when you have a lot of quantity, a lot of water, a lot of moderator, this effect is improved.
Okay, thank you, Carlo. Again, Fernando.
I would like to know how much is the extra dose that you measure at Marambio?
I have not this data here, okay? Because at that time we had only one standard measure dosimeter, so you have the integral, not the spectrum. I don't remember this number now. I have to check.
Yeah, because you told us that this, as we live at this high altitude
Yeah.
in this area, this the South American anomaly, we are exposed to this extra dose, right?
Yeah, this is the you make the difference.
Yes.
Which is the one, and I show you the plot, which is the difference between the sea level, okay, and the one that you get at 405,000 meters.
Yes, but I would like to know or understand if this extra dose is a matter for our health, or is just a lower probability to make some DNA changes or something like that.
No, okay, this is something, okay, this kind of, I know this kind of information, so of course, the extra dose that you get at this high altitude, you get, you are in some way, the evolution, some way of the people living here is already,
Habituated?
Habituated, exactly. Okay. So we don't know exactly which is the extra dose. This is the purpose of this experiment, to make this measurement, which is not really available. Okay. And mainly make this study during the peak of the solar activity, where you will, in the eventual possibility of the disruption of the inner belt, the extra dose that would be arrived here at this high altitude could be very high, but we don't know now how much can be affected. This is the purpose. Of course, it's a serendipitous discovery, because we cannot say that during this solar cycle we will see this effect. Okay.
Excellent. Thank you very much. Another question? Okay. If not, I have a question, probably for Luigi. How do you explain the difference in the spectrum of when you compare the Chakotay spectrum with Chervinia spectrum? I mean, concerning the comparison of the peak due to evaporation neutrons. This one, yeah.
So, as I said before, for the low energy peak, there is a question of the snow that moderates.
For the evaporation?
For the high neutron peak, it is we have a certain number of factors. Of course, the altitude, which is much higher. We have something like 2,000 meters of difference, I think. So the flux of neutron will be higher because we are the depth of the atmosphere that the particles have to is of course lower.
But how do you understand this evaporation? Maybe the people are don't.
Well,
I don't know.
What is the evaporation peak?
Yes, what is the evaporation
This is the peak due to the direct interaction between the neutrons and the atmosphere, the molecules in the atmosphere. So nitrogen or oxygen. These are the neutrons directly produced by this reaction.
Okay, thank you. So thanks again to the speakers. And we can conclude the conference. Thank you.